The nth roots of unity, which is simply solutions to this type of equation, z to the power of n is equal to 1. Most of the time we'll see, but occasionally you might see minus 1 as well. So, if we were to look at the solutions, all the solutions would be evenly spaced around the Argand diagram. We talked about that with roots before. And they would lie on the unit circle because they would all end up having a modulus of 1, because the nth root of 1, doesn't matter what the root is, it's going to be 1. And we'll end up, if you were to join the points up, you'd get a lovely regular sided polygon of n sides. So let's have a look at one. Z to the power of 5 is equal to 1. So using our de Moivre's theorem in reverse, so we can find the roots. Remember, it's 2 pi k plus the argument. Well, 1 is, of course, cis 0, so plus 0, divided by 5. Now, you'll notice I've chosen 5 consecutive numbers, but instead of starting with 0 this time, I've started with negative 2. So I've then gone negative 2, negative 1, 0, plus 1, plus 2. And for this sort of roots of unity idea, that's nice because I'll get conjugates, basically. Is why I've done it that way. And so there's my solutions. Cis 0, which is, of course, 1. Well, that makes sense because 1 to the power of 5 is indeed 1, so that's going to work. Cis 2 pi and 5, its conjugate, cis minus 2 pi and 5. Cis 4 pi and 5, and its conjugate, cis minus 4 pi and 5. So if I was to plot these, there's 1, or cis 0. They're evenly spaced around. So every 2 pi and 5, which is, how many degrees is that, 72? Every 72 degrees, is that right? 360 divided by 5. Yeah, it is 72. So every 72 degrees. So there's our first one, cis 2 pi and 5. But then cis minus 2 pi and 5 is there, it's conjugate, so reflection in the x-axis. Cis 4 pi and 5, and its conjugate. And sure enough, look at this. Hey, pentagon. Ah, nice. And there's the unit circle that they all lie on. They're great fun to play with. So we've got our 5 solutions. So omega is one of those solutions. Now when they say a complex root, what they're basically meaning is not the solution 1. 1 would be a real one. It's still a complex number. But when they say complex root, they're meaning the one with imaginary parts. So we don't know which one. It's just one of those 4. But if it is a solution, we're going to show that omega squared, cubed, it's power of 4, and power of 5 are also the other roots. This is a bit of mathematical magic. You're going to love it. Remember, its solutions to z to the power of 5 is equal to 1. Now, I know that if omega is a solution, then omega to the power of 5 is equal to 1, because I'd substitute it into the equation and I'd get a correct statement. But omega to the power of 5 would then be 1 to the power of 5. Because remember, we just said omega to the power of 5 is 1. And 1 to the power of 5 is 1. So therefore, omega to the power of 5 is a solution. But watch this. Omega squared to the power of 5 would be the same as omega to the power of 5 squared. But omega to the power of 5 is equal to 1. And 1 squared is 1. So omega squared also works when I substitute it in. So it's a solution. Now omega cubed to the power of 5 I could rewrite as omega to the power of 5 cubed. But omega to the power of 5 is 1. And 1 cubed is 1. So w cubed or omega cubed is also a solution. Now what else do we have to show? I've done squared, cubed, I've done power of 5. Omega to the power of 4. Gosh, I wonder how I'm going to do that one. Omega to the power of 4 to the power of 5 is the same as omega to the power of 5 to the power of 4. But you never guess what? Omega to the power of 5 is 1. And 1 to the power of 4 is 1. So omega to the power of 4 works. It's a solution as well. So we have proved that, yep, if omega is one of those complex roots, then omega squared, cubed, power of 4, power of 5 will all be solutions. Okay. Now we're going to prove that if I add them all up, I get 0. Well, I could say they're the sum of the roots. Because remember, we said the roots were omega, omega squared, omega cubed, omega to the power of 4, and omega to the power of 5. They're all our solutions. So the sum of the roots would be minus b on a. But omega to the power of 5 is equal to 1. So I've got 1 plus omega squared and so on. But the equation, b is equal to 0. Because remember, my equation was z to the power of 5. So b would be the coefficient of z to the power of 4. Well, there was no coefficient of z to the power of 4. So it equals 0. Proven. That's one way you can do it. Here's another way. There's our equation, omega to the power of 5 minus 1 is equal to 0. I could factorise that. Remember our a to the power of n minus b to the power of n idea. It would factorise to be omega minus 1 outside of 1 plus omega squared plus omega cubed plus omega to the 4. So either 1 minus omega equals 0. Well, if that's true, omega is equal to 1. But we said omega was a complex root. It wasn't equal to 1. So omega minus 1 can't equal 0. Therefore, the other one must equal 0. So there we go. We prove it that way. But wait. We could do it another way. Okay, 1 plus omega squared plus omega cubed plus omega to the power of 4. Guess what that is? It's a geometric series. Look, you start with 1, and every time you're multiplying by omega. So the first term is 1, the ratio is omega, the number of terms is 5. So sub it into our sum to n formula. I get 1 omega to the power of 5 minus 1 over omega minus 1. But that equals 0 because, of course, we know omega to the power of 5 is equal to 1. And 1 minus 1, 0. So that's another way we could do it. Isn't that great? There's 3 different ways using different topics that we've seen so far this year. One used our polynomials idea, one used factorising, so algebra, and this last one used the series and sequences idea. Isn't maths great? Wants us to create a new quadratic equation. And the roots are going to be omega plus omega to the 4, whatever that is going to be one root. And the other one's going to be omega squared plus omega cubed. Now when we set up a quadratic, remember we said we can create anyway. If we know the 2 solutions, we could do it as x squared minus the sum of the roots x plus the product of the roots. So that's what I'm going to do. The sum of the roots would be omega plus omega to the 4, that's one root, plus omega squared plus omega cubed, that's another root. What's that equal to? Hang on a sec. We just proved 1 plus omega squared plus omega cubed plus omega to the power of 4 is equal to 0. Therefore, omega plus omega to the 4 plus omega squared plus omega cubed must equal negative 1. Move the 1 to the other side. So we now know the sum of the roots is minus 1. Let's have a look at the product of the roots. If I was to expand that all out, hang on, omega 6, 7. Hang on, I know something. Omega to the power of 5 is equal to 1. So omega to the power of 6 is the same as omega to the power of 1. And omega to the power of 7 is the same as omega squared. I've got omega cubed plus omega to the power of 4 plus omega squared. Oh, hang on. That's equal to negative 1. We've already worked that out. So now I can write down my quadratic. X squared minus the sum of the roots, so minus 1, plus the product of the roots. There's my equation that would have those. And when you're playing with these sum of the roots questions, basically, you only know 2 things. You know 1 plus omega squared plus omega cubed going up to whatever the power is equal to 0. And then omega to the power of n is equal to 1. Using those 2 ideas, we should be able to solve any problem. Complex cube root. So complex cube root of unity is a solution to omega cubed is equal to 1. So the roots will be 1 omega and omega squared. Use the fact. Well, I could prove it, sum of the roots and do all that, but they've already told us, look, okay, we know that's going to be true. 1 plus omega squared is equal to 0. 2, evaluate 1 plus omega squared all cubed. Remember, all I know is 1 plus omega squared is equal to 0, but I also know omega cubed is equal to 1. I could expand the whole thing out. I'm not going to. 1 plus omega squared is the same as minus omega. If I move the omega to the other side. Now I've only got to cube one term instead of two terms. Minus omega cubed would be minus omega cubed. Omega cubed is equal to 1. Minus 1 is my answer. Oh, geez, fractions. But hang on, I can make this look a bit nicer, because 1 plus omega would be the same as minus omega squared. And 1 plus omega squared would be the same as minus omega. A lot easier to add these two fractions together. Add them together, I get minus 1 minus omega over omega squared. Minus 1 minus omega. Oh, hang on. If I move 1 and omega to the other side, I'll get minus 1 minus omega. It's going to equal omega squared. And omega squared on omega squared, 1. You might be thinking every answer is 1 or minus 1. Funny, when we're dealing with roots of unity, you'd be surprised how often the answer is 1. We're going to form a cubic equation. The roots are 1, 1 plus omega, and 1 plus omega squared. Now, I know one of the solutions is 1 straight away. So I'm going to write that down as a factor, z minus 1. The other factor then must be a quadratic. And I'm going to use that idea again of, well, a quadratic, that'll be x squared, or in this case z squared, minus the sum of the roots plus the product of the roots. So sum of the roots, if I add the other two together, I'll get 2 plus omega squared. If I multiply the two together, I end up getting 1 plus omega squared plus omega cubed. But remember, we know 1 plus omega squared is equal to 0. So 2 plus omega squared must be 1. And 1 plus omega squared plus omega cubed would leave me with omega cubed, and omega cubed is equal to 1. So there it is, z minus 1, z squared minus z plus 1. Well, if I expand that out, I'm starting to find a cubic equation there. We've got some z squareds that'll cancel. No, they add together. So z cubed minus 2z squared plus 2z minus 1. We're going to solve this equation. Now, I'm sure before this year you would have looked at this equation and gone, gosh, how am I going to do that? Maybe you wouldn't have said gosh, but the essence of the idea was there. But now it's a piece of cake. Watch this. I don't know how to solve this. This is honest. I don't. But I do know how to solve another equation. I know how to solve z to the power of 6 minus 1 equals 0, because that's a roots of unity question. And I also know that z to the power of 6 minus 1 is equal to z minus 1 times the expression they've got there. So, what I know then is these two equations will have the same solutions, but the one they want won't have the solution to z minus 1 equals 0, because that's not part of their one. It'll have all the other answers. So I just have to go, all right, I'm going to find all the solutions to z to the power of 6 minus 1, and then I'll get rid of the solutions they don't want. And they don't want the answer 1. All right, roots of unity. Again, I've put it in conjugate idea. I've gone 0 plus or minus 1 plus or minus 2. Then I just need one more, so I went 3. This is another way of explaining why it's the same thing, because what I could do is multiply top and bottom of this fraction by z minus 1. The top of the fraction is z to the power of 6 minus 1, but of course the bottom of the fraction can't equal 0. So that's another way of explaining why I get all the solutions to z to the power of 6 minus 1, but I won't get the solution z equals 1. Okay, let's work out our solutions from our little formula up there. We'll get cis pi and 3, cis minus pi and 3, cis 2 pi and 3, cis minus 2 pi and 3, and cis pi. I just haven't included cis 0 because cis 0 would be 1. That's the answer we don't want. And in fact, I could work those out because that's an exact value. So there's all the solutions to that equation. Done relatively quickly too, I would think. So how about that? At the start of the year, you would have gone, whew, how on earth? Now, you do it like that. Well, maybe like that. 2 clicks, maybe. Let's have a look at the 1996 problem. They've told us omega is a specific solution. It's the solution cos 2 pi on 9 plus I sine 2 pi on 9. We're going to show that omega to the power of k, doesn't matter what number we substitute in for k, it will always be a solution to this equation. So z to the power of 9 is equal to 1. Again, it's a roots of unity question. I know if I was to solve this, I'd go cis 2 pi k on 9, where k equals 0, 1, 2, 3, 4, 5, 6, 7. I'd stop at 8, but it could be any number. It just had to be 9 consecutive numbers. I'm going to rewrite that. It's de Moivre's theorem in reverse, I guess, if you like. If we had a complex number to the power of k, we said we could make it k theta. Well, I've done it the other way. And look, cis 2 pi on 9, that's what they've told me omega is. And so there we go. The solution is omega to the power of k, where k is 0, 1, 2, 3, 4. In other words, an integer. Prove that all of that is equal to 1, or negative 1, sorry. Sum of the roots idea again, or whichever method you choose to use. I'm going to do sum of the roots. I would imagine that's how I did it. There we go. I know 1 plus omega squared equals 0 because of the sum of the roots. Therefore, move the 1 to the other side. Hence show cos pi on 9 plus times cos 2 pi on 9 times cos 4 pi on 9 is equal to 1/8. All right, it would factorise to be z minus each of those roots. So z minus 1, z minus omega to the 8, and so on, and so on, and so on, and so on. This would factorise to be so. Now, you're looking like, whew, how do you do that so quick? Here's how I did it so quick. Z minus 1 stayed as Z minus 1. No magic there. But notice how I wrote these powers. I didn't go 1, 2, 3, 4, 5, 6, 7, 8. I went 1, 8, 2, 7, 3, 6, 4, 5. I'm grabbing the two numbers that add together to give, in this case, 9. Because they will turn out to be conjugates. So again, when I expand these out, I'll get a quadratic. It'll be minus the sum of the roots. But if I've got conjugates, remember what we saw with conjugates, add them together, you get twice the real part. So I've got 2 lots of cos 2 pi on 9. And then when I multiply them together, I'm going to get omega times omega to the power of 8, which is omega to the power of 9, which is 1, because it's the solution to our month. So we get plus 1. Be very careful. It's cos 2 pi on 9, not cis 2 pi on 9. Cos 2 pi on 9. It's the real part. And so omega squared, the real part, would be cos 4 pi on 9. So the next one's 4 pi on 9. The next one is 6 pi on 9, because it's cubed. And then the last one is 8 pi on 9. All right, I now have an expression. I want to come up with cos pi on 9 times cos 2 pi on 9 times cos 4 pi on 9. And I've got some of that there. I've got 4 pi on 9. I've got 2 pi on 9. Oh, I've got 6 pi on 9. I've got 8 pi on 9. Some of that we can work out. 6 pi on 9 simplifies to be what? It's not a trick question, by the way. 6 on 9 is the same as? That's an exact value. We can work that one out. 8 pi on 9. 8 pi on 9 is an obtuse angle. It would be the same as minus the cos of pi on 9, which is the missing angle that's there. So I can play around with this. Okay. Oh, I haven't done the 8 pi on 9 yet. I've changed the z squared plus z plus 1 because, remember we said this was the cos of 2 pi on 3, which is an obtuse angle. So it's negative, so my minus became a plus. The acute angle would be pi on 3 or 60 degrees. Cos of 60 is a half. Half times 2 is 1. So now that's z squared plus z plus 1. Okay, now let's sort out this. I'm going to let z equal I. I? Why? Because, have a look at each of these brackets. Remember, I want a situation where I'm multiplying cos times cos times cos. I don't want the z squared and the 1. Too messy. Z squared plus 1. How can I make that equal to 0? Make Z equal to I. Because I squared is negative 1. That's why I've chosen to substitute in. So each of these Z squareds plus 1 will become 0. Okay. So we're getting closer now. We've now got the cos times the cos times the cos. Yeah, there's an I in there. Let's just, there's the same expression. We're just on the next page. Let's play around with this a little bit. Common factor of I. You might think we're in the Navy, but we're not. Some people got it. Okay. So I factorised out minus, because I took the negative signs out as well, minus I to the 4. I to the 4 is 1. Okay. Now, on this side, I to the 9 minus 1. Well, I to the 9 is I. So I've now got I minus 1. Oh, I've got an I minus 1 on this side too, so I can divide by I minus 1. We're getting so much closer now. Because now I've taken out the 2 times the 2 times the 2, which is 8. I've got the I to the power of 4, which I've turned into 1. I minus 1 cancelled with the I minus 1. And, of course, then the negative sign as well. I've divided both sides by negative 1. The last thing is to change my cos 8 pi on 9. I'm going to change that to minus cos pi on 9. And eventually I've got my answer. Is that good or what? I mean, how much fun is that? All right. Woo-hoo.